So in this lesson, we're going to take a look at a couple of things. First, we're going to take a look at, well, if I have a cascade and I want some amount of uranium-235 out in my product stream, and I want to have some amount of uranium-235 out in my waste stream, and I have some given amount in my feed, right? How much am I going to need to put in order to get that particular amount of uranium-235 out in both the product and the waste? And then we're going to look, okay, well, given that, how much work is it going to take to make that happen? So let's start with some equations that we looked at in the last few lectures. The first being this one, which is our mass balance, which simply says what goes in must come out. Not only that, but for our total mass, but if we look at our fractional mass, that is, whatever mass of uranium-235 specifically is going in also must equal the mass of uranium-235 coming out. And that is basically equivalent to saying, what's my fraction going in and what are my fractions going out? So we started with these two right here. And then all we're doing, instead of using these variables with the subscript of 35 to indicate that that's what we're talking about, we're going to use those variables, those x variables that we introduced. So this is saying that my feed with some percentage of uranium-235 is equal to the product and the waste with their own percentages of uranium-235. Now, for simplicity's sake, we can just go ahead and ditch the F, the P, and the W's here and just talk about the percentages or those x variables. So if we rewrite this in terms of just the x variables, and then we do a little bit of manipulation, a little bit of algebra, we can come up with an expression like we see here. Now, what this is telling me is for a given amount of product per unit product. So in this case, let's call it 1 kilogram. So if I wanted 1 kilogram of some enrichment of uranium-235 out in my product, and I specified some percentage out in the waste, I could tell you exactly how much feed total am I going to need in order to get those product and waste percentages that I want. Okay, similarly, we can do the same thing and find out, okay, well, if I have those things specified, how much am I throwing away? What's going to be the amount of waste that I'm generating per unit product, or in this case, per kilogram of a particular enrichment? Okay, so these are just going to be our mass ratios. And they're very useful in not just determining, how much work is going to be required, but how much of how much do I need to start with to get what I want at the end? Okay, so I'll clarify this a little bit here in a couple of slides. All right, so if we put it all together, we can come up with an expression that tells us how much work do we need. Now, so S is how much work do we need? S stands for separative work unit. Now, separative work unit's kind of weird. It doesn't have any units to it. It's just purely a mathematical function that tells us the amount of work that we need to separate a binary mixture with a few set parameters. So in this case, our S, how much work do we need? Okay, so we need work to separate out the product percentage that we want. We need some work in order to separate out the waste percentage that we want. And then, of course, we already have work put in with whatever separation we're starting with. Okay, so if we're starting with some feed, which has some percentage, okay, we're simply taking the difference between what's in the feed and then what's in our product and our waste. Now this V of X, we'll call it X sub I. So instead of XW, XP and XF, because they're all the same, that is called a work function. And it, again, is very specific to a binary mixture or a mixture with only two components. So let's take a look at what do we mean by work function. Now, I'll show you the equation that governs this in a couple of slides as well. So a work function just says this: if we have a binary mixture and we start at 50-50, Okay. If we try to get rid of all of one or all of the other, the amount of work that's required, it goes up exponentially. Okay. And it doesn't matter if we're trying to get all uranium-235 in the case of our product or all uranium-238 in the case of our waste stream, right? It takes a set amount of work based on what you started with. Now, imagine that we said, all right, we're going to start with natural uranium, which is 0.0071% U-235. And we want to enrich it to 4% U-235 in our product stream, but we want to try to, keep most of the uranium-235 altogether. So let's lower our waste stream down to about 0.3% or 0.003. So we can plug those numbers into our work functions and we can see, okay, if I'm starting out with a feed of, 0.71%, how much work is going to be required? So first of all, assuming we're starting, assuming you start with a 50-50 mixture, to go from that to 4%, it takes about three separative, about three of the work function. We'll just call it that. It doesn't have any units either. Okay. To separate it down to 0.0071, it would be about a little less than 5 for the work function. And then if we wanted our waste stream, or 0.003, right, that's going lower than all of these other numbers. It's pushing more to one side. So that's going to actually be a bit more. So just slightly less than 6. Okay, so that by itself doesn't really tell you a whole lot. It just says that, okay, the closer I get to one side, right, in this case, the closer I get to uranium-235, or the closer I get to all uranium-238, the more work it starts taking. Okay, so if we look at one side of the graph, let's look over here. 0.003% U-235 means that we have 99.7% of uranium-238. So that's going to put it somewhere up here on our work function. The same thing goes with 0.7% enriched. Okay, that's going to be somewhere over here. Okay, that's going to be 99.3. So both of those numbers are going to be way up here on the curve, which means if we were starting from 50-50, it would take a lot of work to get there. Okay, then we look at 4%. And 4%, it's right about here. Well, actually, that's 40%. 4% is probably right around here somewhere. Okay, so it's going to be up here on the graph, which is not nearly as high as 99.7 or 99.3. So from a 50-50 mixture, it takes a lot less work to get to 4% than it does to get to either 0.7 or 0.3%. Hopefully that makes sense. Now, if we take those same fractions that we're going to be using and put them into those equations where we looked at the mass ratios, we can see that in order to get to 0.4% enriched uranium-235, we would need, for 1 kilogram, we would need 9 kilograms of feed. Right? So just to get 1 kilogram out, we have to put 9 kilograms in. So if we just do some simple math, we subtract 1 kilogram from this total amount of feed that we need, we can see that we're throwing away, in terms of just overall mass, our waste stream is going to have 8 kilograms of material. The last thing is looking at, okay, well, how much work is it going to take for that one product, 1 kilogram of product? And we can see here that that's going to be the number of SWUs that we need, or separative work units, for 1 kilogram output is going to be about 5.2. Okay, and this is very specific to these numbers that we've picked for our cascade. Now, just to see how much difference it makes as we move further and further to 100%, either on one side or the other, so either 100% uranium-235 or 100% uranium-238, we can see that, all right, if we wanted to separate it out to 90%, our work function is telling us it's about 1.8. If we wanted to separate it out to 99%, it jumps up pretty significantly to 4.5. If we then just wanted to eke out just a little bit more to 99.9%, then we see it jump again almost up to 7. So as we start moving up here, it takes more and more work to get smaller and smaller gains in our separation. Okay, that's all this graph really should be telling you, that the more we try to separate out, the harder and harder it gets. So if we put all that together, we can come up with this equation. So we can get our separative work units in terms of unit product. Okay, we're going to be looking at the work function for our unit product, right? So because we divided it out, it won't be there anymore. Then we look at our waste per unit product and the work it takes. And then what do we start with? Well, that's our feed per unit product and the amount of work it would have taken that we don't need to expend in order to start from there. Okay? So to get to this point, again, it's just those previous equations, and we're just doing a little bit of algebra. And here's kind of a way to see graphically how much work do we need for a given set of parameters. So we have our mass over here on the y-axis, and we have our enrichment level over here on the x-axis, right? So the size of the circle is basically representative of how much work. So if we go to, let's just take a given mass, and then we say, okay, so we can pick any one of these levels. So let's just go with 100. Let's say we're starting with 100 kilograms. So if I wanted 10%, okay, it would take this much work. If I wanted 20%, it would take more, 30, 40, 50, 60. And this is starting from natural uranium. And then if we look all the way up here to 70, it's the biggest circle, which means it takes the most amount of work to get to. So let's take it and put it all together. All right, so we've derived our mass, we started with our mass balance equations. We derived our mass ratios. Okay, so let's put numbers in and see if they match up to what we looked at on the previous slide. So again, if I had a feed of 10 kilograms per hour, or just 10 kilograms in general, we'll just use the number 10. And I use those same numbers. So we're starting with natural uranium. We want 4% enriched, but we want only 0.3% in our waste stream. Okay, what is the output, or so how much product are we going to get out at the end? If we put all of those numbers in, we see that our product is going to be about a kilogram per hour. Okay, 1.1 kilograms per hour, or 1.1 kilograms if we were just putting in 10 kilograms. Okay, that's again just using that mass balance. Now let's take a look at how much work do we need to get to the amount of product coming out. Well, we have our cool little equation here, and then this is going to be the equation for that work function, and we're literally just plugging in whatever fraction that we're working with. So if this was going to be the work function for the product, we would be putting the product percentage in for X, or fraction in for X. If we were going to be doing the waste, we would be putting in the X sub W, and the same for the feed. Okay, so putting this all together and throwing the numbers in there, just like you see it, we see that we have so I already did a little bit of math here, but if we just put all of those numbers in and we did the calculation out, we would find that it would, for 1 kilogram of product output, it would be 5.283 separative work units per unit product, which is exactly the same as we see here on this slide when I was talking about it. I pre-calculated these so I could talk about them a little bit earlier than bringing up the whole equation. But it's exactly the same. And that's it. And that's how we go from just doing a very basic mass balance, right? And then going from that to figure out how much do we need of something in to get the stuff that we want out, to, all right, well, for those numbers that we've picked, how much work does it take? And that's pretty much it. So in the next few lessons, we're going to take a look at very specific enrichment technologies, centrifuge, diffusion, that sort of thing. Now, those will be different from each other, and they'll have different separation values or enrichment values. However, to calculate the amount of work that we need, it doesn't matter which one of those technologies that we're using. It all depends on what are our fractions. How much are we going to have in the product? How much is in the waste? And how much is going to be required for the feed?